Thank you very much for the introduction. And also, of course, I would like to thank the organizers for inviting me and for this nice conference, especially Elizabeth, who always says, I am saying nothing when we ask her about other organizers. Okay, as I said, I'll be talking about, in my abstract, about the problem, the following problem. Let us consider some RD and consider two Gaussian random vectors, x with coordinates x1, so on, xn, and y with coordinates y1, and so on, yn. And we assume that they are Gaussian and centered. And let us denote the covariance matrices by with covariance matrices sigma x and sigma y respectively. Okay, and we would like to consider the following question: is it true that if the distribution of the maximum of the coordinates of the first vector coincides with the distribution of the second one, then covariance matrices of these two vectors are the same. Of course, if we if max of x1, xn is equidistributed with max of y1, yn, then sigma x equals sigma y. Of course, if we permute the coordinates of x, then the distribution of x maximum doesn't change. So, of course, we have to take it into account. So, when I say sigma x is sigma y, it means up to permutations. Sorry, in my abstract, I think I wrote up to rotations. Of course, it's incorrect. I meant up to the permutations. Okay, and before, let me start with some historical remarks. History. I think the first one who considered this question was Nadas in 1971. He wrote a paper when he also considered the following notation. He also considered I, capital I, which is the number, which is the index of the maximum coordinate. It is I such that xi is I such that the definition such that xi is a maximum among the coordinates. x1 and so on, xn. And he considered dimension 2, d equals 2. And he proved that not just the maximum, but the joint distribution, we not only know the maximum, the meaning, the value of the maximum, but we also know who contributes to this maximum. So if we know the pair, the distribution of the pair max of xy and the index of the maximum coordinates, then we know the distribution of x. Let me just write it, defines x. Again, up to permutations of the coordinate, of course. And actually, it is a paper, it consists of less than 2 pages. And actually, it turned out to be incomplete. The proof turned out to be incomplete, in some sense, incorrect. But anyway, it has about 47 citations, this paper, maybe because it was the first who considered this problem. And later in 1977, it was a paper by Anderson, Theodore Anderson, the well-known statistician, Anderson from Stanford, and Gurria. Actually, he is from the University of Alberta. Maybe someone of you know him, but I don't know him. In 1977, they considered actually the same problem, and they started from the motivation from the economy. Anderson said that there is a big demand from the economists who would like to consider this problem, and in particular, in this paper he presented the following model, and this model came to him from the well-known economist Takeshi Amemiya. Takeshi Amemiya. He is also from Stanford, like Anderson, and he's still alive, as far as I know. And he described the following econometric model of the demand supply of some commodity. He considered two quantities, x1, it is alpha 1 plus beta 1 p plus sigma 1 n1. It is a quantity for demand for some commodity, where p is price of this commodity. So it depends, alpha 1, beta 1, some non-random parameters, and sigma 1 and 1, some kind of noise, and 1 is standard Gaussian variable. And of course, beta 1 must be positive. The greater price, the greater, oh, so sorry, negative, the greater price, the less demand. And x2, it is alpha 2 plus beta 2 p plus sigma 2 n2. It is supply of this commodity. And here, of course, beta 2 must be positive. And the quantity which is of interest to economists is the mean of x1, x2. It is nothing but how much this commodity will be sold. It is minimum between demand and supply, sold commodity. And the economists, they're interested in the question, is it true? Then the distribution of the sold quantity of the commodity actually defines the parameters of the above model. So it was the motivation for Anderson, and they together with Gurria, they proved the following result. Again, they considered D equals 2, and they proved two things. First one is that max of x1, x2 defines x when the first one, actually they considered not only centered. In my talk, I will consider only centered vectors, but in case D equals 2, they considered non-centered, but negatively correlated with row 1, 2 negative. They proved that this max, the distribution of max defines the distribution of X. And second paper, actually it was two papers. The second paper was that it is always again in dimension 2, of course, for centered X. And I think that they didn't know about the paper of Nadas, and actually in the first paper with this result, they gave no reference at all, which is funny. And in the second, it was only 3 references, and one of them, of course, the first paper of themselves. Okay, the next result was due to Bash and Gaussian in 1978, they considered the case, completely considered the case d equals 2, and they prove this that our equation is positive, that Max defines distribution of Max defines the distribution of X for all non-centered, And also they considered the case, maybe for the first time, they considered the case d equals 3. And by the way, before going further, in the paper of Anderson and Gurye, how did they prove this? They actually considered the asymptotical distribution of the tails of the Max, and they proved that if asymptotic for X and for Y, they have the same asymptotic distribution of the tails, then it defines the parameters of the model. And actually, as far as I know, all known results, which I present later, actually uses the same technique. Everybody investigates the asymptotic of the tails distribution, the asymptotic distribution of the tails, and then compare. And from this, the fact that the maximums have the same asymptotic tail distribution, they conclude that the parameters are the same, and which actually is highly non-trivial. Even in two-dimensional case, it is not very easy, and in three-dimensional case, it's much more complicated. And the aim of my talk is to present some geometric model which will easily explain almost all known results geometrically without any asymptotic analysis of the tails, and also led to obtain some new results, but I will tell later about it. Okay, and also Bash and Gaussian, they considered three-dimensional case, and they proved that for the case when correlations satisfy the following inequality, mean of sigma I over sigma j and sigma j over sigma I. They didn't comment this this condition, but later when I will give you some geometrical model, I will comment this condition has a very clear geometrical sense actually. And they prove that in this case, again, the joint distribution, not only max, but also the number of the coordinate, maximal coordinate, the index of the maximal coordinate defines X. Okay. And later, El-Nagar and Mukherjee in 1999. They again consider the case d equals 3 and X-centered, and they considered the case when all correlations are the same. So if rho ij, some constant rho for all ij is the same, then max of the coordinates defines X. And not very recently, or not relatively recently, sorry, Davis and again Mukherjee in 2006, they again in three-dimensional case, they considered negative correlations. Actually, of course, this condition Oh, sorry, this condition, negative correlations, implies this condition. They considered negative correlations, X-centered, and also in their paper, they considered different variances, but they claimed that actually it doesn't matter for them, but proved only for different variances. Again, prove the same, that max xi defines x. And the last result which I'll cite, it is due to B and again Mukherjee in 2010. They consider the same thing as previous, but X non-centered. They generalize the previous result for non-centered. Okay, and as I said, in my talk, I'll consider only the result when X is centered vector. And actually, to the best of my knowledge, even the case D equals 3 is open in full generality, without any assumptions. That it is still open question. Is it true without any assumptions on the correlations, even for centered X, full generality. Okay, and in okay, as I said, now I'll present you some geometrical model for this question. Actually, I will use very elementary and very well-known trick, which all of you must know. But surprisingly, it helps to, in some sense, simplify, greatly simplify this problem, and I will show you in a moment why. Okay, so we have again X, is X1 and so on, XD centered, and our covariance matrix X sigma X does a matrix Xi Xj Ij from 1 to D. And of course, since it is symmetric positive definite, it has the following representation. It is some gamma transpose gamma, where gamma, we denoted the columns of gamma by x1, x small x, and so on. They are of course non-random. XD, their columns. Okay, and consider, let's denote by G be a standard Gaussian in RD. Standard Gaussian vector in RD. Okay, and then it is very easy to see that our X, since it has the following covariance matrix, it is equidistributed with the following vector. The vector with coordinates scalar product of G x1 and so on, scalar product of G xd. Because this vector has the same covariance matrix. Of course, it is centered and it has the same covariance matrix. Okay, maybe it will take 1 minute when it has the same covariance matrix. It is just, we have element ig of its covariance matrix is scalar products gxy, scalar product gxj. It is just by definition of a scalar product, sum k from 1 to d, k's coordinate of g, which is standard Gaussian variable, and k's coordinate of xj, and the same for x oh sorry, not xj, xy, and the same for xj. The same for xj. G case coordinate come from 1 to d, case coordinate for g, and case coordinate for xg. Okay, and using the coordinates of g are independent standard Gaussian variables, we have that just it is just the sum k from 1 to d xik xjk. Okay, and it is of course scalar product of our vectors xi xj, and they are by definition the ij element of the matrix gamma t gamma, which is the covariance matrix of x. So we have that x, the left hand side of this and the right hand side has the same distribution. Okay, so from that we have that max of the coordinates of vector x is equidistributed with the max of the right hand side here, the max of okay, let it be like g xi. Okay, and now let us remember the remarkable property of the standard Gaussian vector. All of you know that it can be decomposed like the product of its radial part and the uniform distribution over the sphere. And moreover, these two components are independent. It is characterizing property of the Gaussian distribution. So we have G, it is norm G multiplied by G over G. And the second term is of course uniformly distributed over the unit sphere. So it is just by theta, which is uniformly distributed over S n minus d minus 1. D minus 1. And they are, which is crucial for us, they're independent. Okay, so from this we get that max xy, it is just by distribution the product of the norm of G and the max of theta xi. And the same thing can be done for max of y. Max of y. It is equidistributed G and max of theta y I. And since okay, and we know that these two guys, max of xi and max of yi, are equidistributed, and it's not hard to prove that this is, since these two factors are independent. From this we can conclude that actually we can cancel out this factor, and we have that the equivalent formulation of our problem. Does distribution of max of theta xy given x1 and so on xd from RD, that's distribution of max theta xy, where theta is uniformly distributed over sphere, as I said, defines the shape of its convex hull, defines convex hull of x1 and so on xd. It means define these points up to rotations and reflections. From these points, we want them that they uniquely define the covariant matrix, the gram matrix. It means that we need only their norms and the angles between them. So it means that that their convex hull is defined uniquely up to rotations and reflections, which do not change norms and angles between these vectors. So it is equivalent formulation of the problem. Okay, and let me consider this problem. So we have two now. We have let it denote by x. To the random vector x corresponds the simplex. It's the convex hull of x1 and so on xd. And by the way, this max of theta xy, of course, it is nothing but the support function of our simplex convex hull of x1 and so on xd. So we have a question: is it true that the distribution of the support function defines this for the shape of the simplex?
Dim, I just wanted to ask, you have d vectors in d-dimensional space?
Yes, it is important. Our simplex is degenerate. It's not of full dimension. Yes, thank you. Okay, and the second simplex corresponds to the random vector y. It is convex hull of y1 and so on yd. And we know that let be mu, it's Haar measure on the sphere, probabilistic Haar measure on the sphere. The mu of theta such that max of theta xi at most t, it coincides, it's the distribution function of the support function of the first simplex is the same as the measure of theta such that max of theta y at most t. Okay, and from this we would like to show, try to show that this simplex Sx and Sy essentially are the same. First of all, we would like to consider the question: what is the range of hx of theta? For convenience, let us order the norms of our x's. So we assume that without loss of generality, x1 is at most and so on is at most xd. And what is the maximum of the support function? Of course, it is, in our case, it is the norm of xd, the maximum norm of our. On the picture, that is looks like it happens in the following case: when we have, this is the origin, we have some x2, x3 with the maximum norm, among them x1, and of course when, and there is a direction theta, and of course when our vector with the greatest norm is collinear with theta, then when our support function achieves its maximum. And so and of course this maximum is the norm of x, norm of x3. Okay, and what about the minimum? The minimum is also not very difficult to see. What is the minimum? The minimum achieves on the following picture: when we have the origin here, theta again to the right, And our points, I show it in R3, but in ideas it's all the same, of course. Our points are looks like this. This is our simplex, and if we take a perpendicular from the origin to our simplex, because it is of dimension d -1, we can do this, and this perpendicular must have the opposite direction to theta. So, and in this case, the mean of our support function, of course, it is the distance between 0 and our simplex as x. Okay, and of course, if we consider the vector y, and if its support function has the same distribution, it has to have the same mean h. Sorry. Hello.
It seems we got a problem. You probably try to reconnect. Ah, here he is. Okay.
Sorry, my institute internet fell down, so I'm switching to my mobile. I'm sorry. Do you see my screen?
Yes.
Okay, thank you. So sorry for this. And okay, so our simplex sy and sx at least have the same maximum norm of xd and yd, and also have the same distance to the origin. Of course, it's not enough to identify them to make them the same. But what also we can consider? Also, we can consider the following thing. Consider the behavior of hx near its maximum. Let us consider this. For simplicity, let us assume that the previous norm is strictly less than our maximum norm, just for simplicity, and consider the measure of points, which is such that x of theta is at least our maximum meaning. Let us denote the maximum meaning by h1 and the minimum by h0 is at least h1 minus some epsilon, where epsilon is small. It is the behavior, the distribution near the maximum, small. When it is small, actually, what is this set actually? It is a set is nothing but the cap, spherical cap, because we have the measure, it is the same like xd theta at most, xd minus epsilon, and divided by the norm of x, it is the same like the measure of xd over norm of xd, scalar product with theta, is at least 1 minus epsilon over xd. Okay, And of course, it's nothing but the cap. And the measure of such theta is the measure of this cap. So we have it is a cap. We have somewhere we have cap which for small epsilon, and this cap for small epsilon for our simplex Sx must be the same as a cap for small epsilon as a cap for Sy, because they have the same distribution, the support function of Sx and Sy. And of course, for small epsilon, it holds because the norm of xd is the same that the norm of yd. So they start from the same moment in time when, and actually for small epsilon, the caps are the same. Okay, when epsilon starts to grow, then the second point with norm xd minus 1 comes to play, and another caps appear here. And of course, if another cap doesn't appear here, then the summand area of these two caps would be different. So simultaneously, another cap must appear here on the right picture. It means that the norm of xd minus 1 is the same as the norm yd minus 1, because they appear simultaneously. And it might happen that at some moment they begin to intersect. Again, it must start intersecting simultaneously, because otherwise the area of the union will be different. And it means that the angle between xd and xd minus 1 the same as the angle between yd and yd minus 1. But it is only if the life is ideal. And if everything works like this, we would prove our conjecture in full generality for in all dimensions. But actually, we can consider the following obstacle. It might happen that we have our first cap here, corresponding to xd and corresponding to yd here, and the second cap corresponding to xd minus 1 can appear here, actually, here, and here. And in this case, they do not have to appear simultaneously, because they actually do not affect anything if they appear inside the cap. Okay, and actually, it is the main obstacle. There are a couple of two, but I don't have time to discuss them. And concerning this obstacle, when the cap corresponding to xi can appear inside the cap corresponding to xj. It is very easy to check that it happens when we have on the picture xi here, xj here, and when we draw a line through these two vectors and take a perpendicular, and this happens exactly when these 2 points from the one side of this perpendicular. Only in this case, one cap appears inside another. So it is a bad case, and actually this case corresponds, and good case in this case corresponds exactly to this condition which I mentioned, exactly to this condition which was necessary to these guys. So if this condition hold, then this case, then this obstacle do not occur. And when this condition hold, every new cap appears outside other caps, and this is good for us. And in particular when all correlations are negative, we have this condition. It is also good, and actually this is the most case which was considered. And moreover, let us look at this result. In dimension 3, these guys considered the result of when correlation functions are all equal. From this geometrical argument, which I said, first of all, this condition holds, so all caps are outside in other caps appears. And moreover, using that all angles are the same, from this our geometrical argument, we can easily generalize this to all dimensions. Actually, this from our geometrical argument, we have that this result holds in any dimension. And the last thing, I don't have time to talk about it. Actually, using the more subtle analysis of our support function, not at the maximum, but near the minimum, actually, using the analysis of the behavior of this function, it is, I can prove that dimension 3 actually holds in full generality, actually using this geometrical argument. Okay, so I think my time is up.